Welcome to the DIY Honda Garage channel. The Diagnostic Trouble Code, DTC P16E3, is specific to the Honda HR-V models from 2016 to 2022, indicating a PGM-FI-Battery sensor LIN communication error. This error is primarily associated with issues in the communication line of the battery sensor. The Powertrain Control Module, PCM, communicates with the battery sensor over a local interconnect network, LIN. A failure in this communication can lead to significant performance issues and can affect multiple vehicle systems because the battery sensor provides critical data about the vehicle's battery status. The battery sensor is typically located near the battery, and any abnormalities may stem from loose connections, damaged wires, or faults in the sensor itself. Understanding the root cause is key to effectively resolving the issue, so a structured troubleshooting approach is essential. The error description for DTC P16E3 involves a malfunction in the communication line between the battery sensor and the Powertrain Control Module, PCM. The 12-volt battery sensor monitors the electrical status of the vehicle's battery, providing vital data for the engine management system. The PCM utilizes this data to make real-time adjustments to engine performance and efficiency. LIN, which stands for Local Interconnect Network, is a communication protocol that facilitates the exchange of information between different components in the vehicle. A fault in this communication can impede the PCM's ability to properly assess battery conditions, leading to performance issues. The battery sensor is located close to the battery, making it easily accessible for inspection and testing during diagnosis. Several potential causes can lead to DTC P16E3 being triggered. Loose terminals at the 12-volt battery sensor can disrupt communication between the sensor and the PCM, impacting signal integrity. Short or open circuits in the wiring are also common culprits. These can occur due to wear and tear, improper installation, or damage from environmental conditions. A faulty battery sensor itself could be the source of the problem, where the sensor fails to provide accurate data. Additionally, if the PCM software is outdated or contains bugs, this may lead to erroneous readings or communication errors. Each of these causes can be systematically tested and ruled out during the troubleshooting process. When DTC P16E3 is present, the driver may notice several symptoms that indicate a problem within the vehicle's electrical system. The check engine light will typically illuminate on the dashboard, alerting the driver to an issue that needs attention. Additionally, poor engine performance may become evident as the PCM struggles to optimize engine parameters without reliable battery data. Drivers might also experience inconsistencies in battery charge levels, potentially leading to starting problems and reduced functionality of electrical components. Furthermore, intermittent electrical faults may occur due to communication losses, affecting various systems in the vehicle. Recognizing these symptoms can help in swiftly addressing the underlying problem through appropriate troubleshooting steps. The first troubleshooting step involves problem verification. Begin by turning the vehicle to the on mode, ensuring that all electronic systems are active. Using a Honda Diagnostic System, HDS, clear any existing DTCs, including P16E3, and wait for about 10 seconds to refresh the vehicle's diagnostic data. After this, check for any pending or confirmed DTCs. If P16E3 reappears, it indicates a consistent failure, and you will proceed to the next troubleshooting step to further investigate. However, if it does not reappear, this suggests an intermittent fault may be present, prompting an examination of all related connections for any poor or loose terminals at both the 12-volt battery sensor and the PCM. In the second troubleshooting step, once the initial DTC check is carried out, you need to check once again for any pending or confirmed DTCs with the HDS. If DTC P16E3 emerges, this implies there is a second communication error, specifically related to the ACG, alternating current generator, LIN communication. You would then proceed to the next defined step for investigating this new error. On the other hand, if DTC P16E3 does not appear, you will move on to the next step in your diagnostic process. This step is critical in isolating the specific error and preventing unnecessary tests in parts that are functioning correctly. At this point in the troubleshooting process, you will need to assess the wiring and connections linked to the 12-volt battery sensor. First, turn the vehicle off lock mode, ensuring safety while you work. Next, disconnect the 12-volt battery sensor 3P connector. For testing, check continuity between test points 1 and 2, with test point 1 being the 12-volt battery sensor connector number 3, and test point 2 being a solid body ground. This test will confirm whether continuity exists in the LIN wire. If there is continuity, this indicates that the LIN communication pathway is intact, and you would advance to the next step for further wire checks. Conversely, a lack of continuity suggests a possible disconnection or break in the LIN wiring, warranting deeper investigation. In this step, you will focus on identifying whether the LIN wire is shorted, which may disrupt communication. Use the HDS to jump the SCS line. This is a service check that allows continuity testing under controlled conditions. Continue checking for continuity between the 12-volt battery sensor 3P connector terminal number 3 and body ground, while disconnecting the connectors of components like the alternator and PCM one at a time. During this procedure, you will observe if continuity ceases when any of those connectors are disconnected. If the continuity is lost, it indicates the LIN wire is functioning properly, and you need to replace the part causing the disruption. If the continuity remains throughout, you may need to repair a short in the LIN wire among these components. The next step in the troubleshooting process brings you back to inspect the battery sensor functionality. Reconnect the previously disconnected 12-volt battery sensor 3-pin connector to prepare for another test. Then proceed to disconnect the alternator 1-pin connector to avoid interference in the circuit checks. Similar to previous steps, check for continuity. This time, you will be testing between the alternator 1-pin connector number 1 and body ground. If continuity exists, it suggests the 12-volt battery sensor is likely faulty and needs replacement. If there is no continuity, you would advance to further wire checks to ensure all connections and wiring are intact. In this step, you will further assess the integrity of the wiring linked to the battery sensor. Start by jumping the SCS line with the HDS once more. Then, disconnect the 12-volt battery sensor 3P connector and the PCM connector B51P, ensuring that no signals are being sent during the test. Check for continuity between the designated test points, connector B51P number 31, and the 12-volt battery sensor 3P connector number 3. If continuity is confirmed, it indicates that the LIN wire is in proper condition. In such cases, you should check whether the PCM has the latest software update. An update could potentially solve the issue, or substituting in a known good PCM can also clarify whether the PCM itself is the source of the problem. The seventh troubleshooting step involves checking the fuse pertinent to the battery sensor circuit. Start by turning the vehicle off, allowing for safe inspection. Locate fuse numbered B18, identified as a 10A fuse, positioned in the underhood fuse/relay box. Inspect the status of the fuse carefully. If it appears blown or damaged, replace it and address any underlying issues that may have caused the short circuit. Should the fuse remain intact, this indicates that the issue lies elsewhere, prompting you to proceed to the next step in your diagnostic pathway. Performing this fuse check is critical, as a blown fuse can impede communication between essential components. Following the fuse check, this step focuses on verifying the integrity of the +B horn wire configuration pertaining to the battery sensor. Accurately disconnect the 12-volt battery sensor 3P connector to prepare for the voltage measurement process. With the vehicle still in off-lock mode, measure the voltage between test points, the battery sensor connector number 2, and a known good body ground. Verification of battery voltage will confirm whether the +B horn wire is intact. If battery voltage is present, the wire integrity is satisfactory, and you would proceed to the final verification steps. However, if no voltage is detected, this indicates a potential open circuit in the wiring that needs to be repaired to restore proper communication. The final troubleshooting step involves one last comprehensive check of the LIN communication pathway. Start by ensuring the vehicle is in the off-lock mode for safety. Jump the SCS line with the HDS to facilitate the continuity check. Then, disconnect the PCM connector B51P one last time. Engage in a continuity check between the PCM connector B51P number 31 and the 12-volt battery sensor 3P connector number 3. Confirming continuity at this point means the LIN wire is functioning properly. If continuity exists, you may be required to replace the 12-volt battery sensor to resolve the issue permanently. If continuity is absent, a repair to the open wire between the PCM and the 12-volt battery sensor must be conducted to ensure proper communication functionality. After completing the necessary repairs or parts replacements, the final verification stage is crucial to ensure the problem has been adequately addressed. Start by clearing any DTCs using the HDS, including DTC P16E3. Following this, it is essential to conduct a thorough test of the vehicle's operation, particularly monitoring for any signs of the previous issues, such as check engine light illumination or performance irregularities. This hands-on testing will provide vital feedback regarding whether the communication error has been resolved. In addition to operational checks, maintaining a watchful eye on the vehicle's performance in subsequent days is an effective strategy for ensuring that the solution is durable and effective. If all tests pass, you can confidently conclude the repair has been successful. Preventive maintenance plays an essential role in ensuring the longevity and reliability of the vehicle's electrical systems. To prevent issues similar to DTC P16E3, it is advisable to conduct regular inspections of all electrical connections, ensuring that terminals are tight and free of corrosion, particularly around the battery and associated sensors. Regular cleaning can help maintain optimal conductivity. Additionally, staying up to date with the latest PCM software updates provided by Honda is essential, as these updates not only improve vehicle performance, but can also address known issues in the system's communication protocols. Establishing a regular maintenance schedule can prevent future occurrences of communication errors and enhance the vehicle's overall efficiency. In summary, effectively diagnosing and resolving DTC P16E3 requires a structured approach, understanding both the components involved and the communication protocols at play. Identifying symptoms related to LIN communication errors can provide critical insight into underlying issues. The troubleshooting steps emphasize the necessity of checking connections, verifying wiring integrity, and potentially replacing faulty components to restore proper function. A well-executed repair process, followed by thorough verification and preventive maintenance practices, will ensure the longevity of the battery sensor and the overall electrical system's health. Thus, mastering these troubleshooting techniques can lead to greater reliability and performance in your Honda HR-V models from 2016 to 2022. Please like and subscribe to the channel. See you next time!